Okay, so here in this video, we will see for ourselves a peculiar situation which is already in place in relation to the distinguishability or indistinct in relation to characterization for a canonical ensemble and a micro-canonical ensemble. So basically, in our previous discussions, previous videos, we know that the micro-canonical ensemble and the canonical ensemble do differ from each other. Right? Why? Because in the canonical ensemble, you do allow some kind of an energy to change between the elements, which means that you do allow an energy fluctuation within the system. So, but in the case of micro-canonical ensemble, you are not allowing that. Whereas it is actually a realistic, non-realistic situation where you don't allow any kind of energy fluctuations. Okay, so that was the picture in which we started this journey into the canonical ensemble. And what happened was that we made all the formulations for the canonical ensembles, and we derived, for example, in an ideal gas. In the ideal gas, the expression for the entropy for 3D ideal gas, right? The expression which we wrote was S is equal to Nk ln V by N 2 pi mkt divided by h squared raised to 3 by 2 plus 5 by 2. So this was the expression which we wrote, or you can mathematically you can reach something like this. Not something, you can reach an expression of this kind. But if you remember, based after our Gibbs paradox discussions and all that, those things, after supplying all the corrections, we reached the same expression for the entropy for the ideal gas there also. So there at that point of time, we were talking about the micro-canonical ensemble. So what happened is that the entropy expression, which we derived based on the micro-canonical ensemble situation and the canonical ensemble situation for a classical ideal gas, turned out to be exactly same. But how can this happen if we are dealing with two different situations, right? How can the expression turn out to be the same, even though we are our assumptions are different in both in those kinds of ensembles? So this is a very curious situation. We can get out of this riddle if we prove that at some particular kind of situations, both the micro-canonical ensemble and the canonical ensemble gets into, or micro-canonical ensemble can be approximated to a canonical ensemble or vice versa at some kind of a particular situation, right? So let's try to do that. For that purpose, we take into our consideration the central point which distinguishes between the canonical ensemble and a micro-canonical, which is the energy fluctuations. Energy fluctuations in canonical ensemble and we do it in correspondence to microcanonical. Ensemble. So that is what we are trying to do, right? So how do we do that? Let's start with the expression for our average energy of the system. So what was the average energy of our of the classical ideal gas? Energy of an ideal gas U is equal to summation over S ES e raised to minus beta ES divided by summation over S e raised to minus beta ES. So this was the expression which we use for the energy, the average energy of an ideal gas, right? Now I can, what I do is that I take the differential with respect to beta, dou u by dou beta, right? What I do is that d by dx of u by v, right? That kind of identity I will use, because here we have quantities which needs to be considered as u by v functions. So we will do that. So therefore I apply that identity over here. Sum over s e raised to minus beta. Yes, you can try doing it yourself. E raised to minus beta es sum over s es e raised to minus beta es into minus es. D by dx of u by v is v into dou u by dou x minus u into dv by dx, right? So we do that here, minus sum over s es minus sorry, e raised to minus beta es into sum over s e raised to minus beta es into minus es divided by v squared. So here the v squared means the summation over s e raised to minus beta es the whole square, right? So this is the expression, and this is how I will apply the identity, right? So now I will try to simplify this. I can write dou u by dou beta equal to minus sum over s es squared e raised to minus beta es divided by sum over s e raised to minus beta es plus sum over s es e raised to minus beta es the whole square divided by sum over s e raised to minus beta es the whole square, right? Which I can write it as sum over s es square e raised to minus beta es divided by sum over s e raised to minus beta es plus I will take the squares together, sum over s es e raised to minus beta es divided by sum over s e raised to minus beta es the whole square. This one I can take it as so there's a minus over here, right? This minus, I forgot to take it down. So this expression, now I can write it as equal to minus expectation or average es squared plus this one is expectation es, right? Whole squared. So this is how I do that. So this is dou u by dou beta. I can, or otherwise I can write minus dou u by dou beta is equal to expectation es squared minus expectation expectation es the whole squared no, if I made a mistake because I take the minus over here, so let's not do that. Es squared minus expectation es the whole square, which is actually reminds me of the basic expression of the variance of a quantity of the quantity called es, which I write as delta es. So basically this is the variance, right? So that's it. We continue in the next video.